Energy is one of those concepts we use all the time. But what exactly is it? In physics, energy is defined as the ability to do work, which means applying a force over a distance or causing some kind of change. Whether it's the light coming from your screen, the heat from a fire, or the power of a battery, all of these are just different forms of energy. Understanding how these forms are related is the key to mastering the most important law in all of science, the law of conservation of energy. When we talk about mechanics, the study of motion, we focus on two main forms of energy. The first is kinetic energy, which is the energy of motion. If something is moving, it has kinetic energy. The second is potential energy, which is stored energy. Think of it like potential, something that has the potential to move later. Together, these two forms make up an object's total mechanical energy. Let's focus on one type of stored energy, gravitational potential energy, e.g., imagine holding a heavy book high above your head. It's not moving, but it certainly has the potential to do work if you drop it. That stored energy is proportional to the object's mass, the acceleration due to gravity, and its height. This is why a wrecking ball, when pulled high above the ground, has a huge amount of stored energy, ready to be unleashed. Now for kinetic energy, EK, the energy of motion. If you want to calculate how much kinetic energy something has, you use the equation half mv squared. Notice that the velocity, or speed, is squared. This means that if you double an object's speed, you actually quadruple its kinetic energy. This is why driving a car just a little bit faster makes the stopping distance dramatically longer. The car has much more energy to dissipate. Here is the big idea, the law of conservation of energy. It states that energy can never be created out of nothing, nor can it be truly destroyed. If you start with 100 joules of energy, you will always end up with 100 joules of energy. All that happens is that the energy transforms from one form to another, like electrical energy turning into light energy in a bulb, or it transfers from one object to another. The total amount is a constant throughout any process. A perfect example of this transformation is a roller coaster. When the car is at the very top of the hill, its speed is low, so its kinetic energy is low, but its height is maximum, so its potential energy is maximum. As it plunges down, the height drops, reducing potential energy. But where does that energy go? It transforms directly into kinetic energy, making the car speed up dramatically at the bottom. It's a constant, balanced exchange between Eg and Ek. To study conservation properly, we need to define the boundaries of our experiment, which we call the system. A system could be a single object, like a ball, or a collection of objects, like the ball and the earth. Everything outside of that boundary is the surroundings. When we model energy, we track what happens inside the system and what energy flows across the boundary. For this standard, we focus on the closed system. In a closed system, matter can't escape, but energy can still be exchanged with the surroundings. An isolated system, which is the perfect model of conservation, is where neither energy nor matter can escape. Though true isolated systems are almost impossible to create perfectly in the real world. By modeling a system as closed or isolated, we can simplify our analysis of energy flow. In a perfect, closed system, the total initial energy equals the total final energy. We can write this simply as energy initial equals energy final. This means if you account for all the forms, kinetic, gravitational potential, thermal, chemical, etc., the numbers on both sides of the equation must match. The energy just reshuffles its identity within that closed box. How does energy cross a boundary or change forms? One major mechanism is work. When you push a heavy box a certain distance, you are doing work on that box, and in the process, you are transferring chemical energy stored in your muscles into the kinetic energy of the box. Work is simply the mechanical way energy is transferred, and since it's energy, its unit is the joule. Another critical way energy is transferred is through heat. Heat is not a form of energy itself, but rather the process of transferring thermal energy due to a temperature difference. If you touch a hot stove, thermal energy is transferred from the stove to your hand. When we analyze a system, we have to account for any heat flowing into or out of it, as this changes the system's total energy, just like work does. In the real world, you might notice that a moving object eventually stops. Did the energy disappear? No, it was dissipated. This lost energy, which is usually due to friction or air resistance, is transformed into thermal energy, or heat. Think of rubbing your hands together. Your kinetic energy turns into heat, which then often radiates out into the surroundings. This thermal energy is still conserved, but it's no longer easily usable for mechanical tasks. The concept of energy conservation directly leads to understanding efficiency. Efficiency is a measure of how much of the energy we put into a machine, like a light bulb, actually gets converted into the useful output, in this case, light. Because every transformation creates some unusable thermal energy, no machine can ever be 100% efficient. The less energy converted to waste heat, the more efficient the device is. Mechanical energy is not the whole story. Chemical potential energy is the energy stored in the very bonds between atoms and molecules. This energy is released during chemical reactions, like when you burn gasoline in a car engine, or when your body breaks down food. This stored energy is what powers every single biological and technological process on Earth. Another incredibly useful form is electrical energy, which is the energy associated with the movement of charged particles. Its brilliance lies in its versatility. Electrical energy is easy to transfer over long distances via power lines, and can be easily converted into almost any other form. Kinetic energy in a blender, light energy in an LED, or thermal energy in a heater. The law of conservation applies to all of these forms. Take a battery-powered flashlight. The chemical potential energy in the battery is transformed into electrical energy, which is then transformed into light energy and thermal energy by the bulb. If you measure the joules of input chemical energy, it will equal the total joules of light and heat produced. The energy is simply following the chain of transformation. To help visualize the conservation of energy, we often use models like a Sankey diagram or simple bar charts. These diagrams show the total initial energy as one large bar, and then show how that energy splits into different output forms like kinetic, potential, and thermal energy, or how work and heat are added or removed from the system. These models are the best way to satisfy the HSPS31 requirement to illustrate energy flow. When we analyze a real-world system, we often see that the final mechanical energy is less than the initial mechanical energy. For example, a bouncing ball won't return to its starting height. Why? Because the difference, that lost energy, was transferred out of the mechanical system as heat and sound. The key insight of the conservation law is realizing that this difference must be accounted for by the incoming and outgoing energy transfers, like work done or heat dissipated, as the standard states. Understanding energy conservation helps us quickly dismiss the idea of the perpetual motion machine, a device that runs forever without an external source. It's a fun idea, but impossible. Due to the unavoidable presence of friction and air resistance, some useful energy is always being converted into unusable thermal energy and transferred out of the system. Eventually, the machine would simply run out of useful energy. In the end, the law of conservation of energy is the ultimate bookkeeping rule of the universe. The total amount of energy is constant, but its quality or usefulness changes as it transforms into heat. By using models of closed systems and tracking the energy that crosses the boundary through work and heat, we can accurately predict and analyze every energy transformation from the smallest cell to the largest power plant.